Yes. So, so in the last class we discussed about the Einstein's photoelectric equation, right? The different cases. What is the Einstein's photoelectric equation? E is equal, sorry, h mu is equals to half mv square, right? Yeah. So h mu is equals to h mu naught plus half mv square. Listen here. H mu is what? It is incident energy. Correct, right? Energy, the light rays which are falling on the metal surface. It's a, the, for example, it's a metal plate which is emitter plate. So the energy of the incident rate is h mu. E is equals to h mu. Correct, right? Now, as the light rays incident on the metal surface, what happens? The electrons will come out. The electrons will come out. Why electrons are coming out? Because the energy which is incident on the metal surface, which is h mu, is used by that energy, okay, and even the momentum. The total energy and total momentum of the light particles, that too they are photons, okay, that's what Einstein says, that photons will enter inside the metal plate and they will collide with the electrons. That electrons will absorb energy and also momentum. So energy is also conserved, momentum is also conserved, okay, both are conserved quantities. So you can say energy and momentum energy is E and momentum is P. Okay, both are conserved in photoelectric effect. Both are conserved. Okay, so I explained last class, right? Okay, if it is there, I'll just show you. See, think that is, it's not there, huh? Okay, it's not there. Yeah, so both are conserved. Energy and momentum. So energy cannot be lost. It will not lost. Whatever energy it will give, whatever energy will come from the light source, part of the energy is used to come out, used by the electron to come out from the metal surface, and the remaining part of energy is used to move with maximum kinetic energy. That's what the part of energy, incident energy, okay, this is incident energy, incident light energy, incident light energy is used to come out from the metal surface. That's what this is, incident light energy. And what is this? Is work function. What is this? Work function. This one I am talking, work function. This is the incident energy. This incident light energy part, small amount, is used as a work function. What is work function? It's the minimum energy needed to remove the electron from the metal surface. Understood? This total energy, some energy is used to do remove the electrons, and whatever the remaining part it will use to move with some maximum velocity or with some kinetic energy V. That's what half mv square. This is what Einstein says. And in the last class we discussed what Einstein explained. Correct, right? Okay. So h mu is equals to h mu naught plus half mv square. Understood? Now, so Einstein says this energy h mu, h mu is the incident energy, and this h mu and this h mu naught, that means work function plus half mv square is there, no? Okay. So this is the kinetic energy. This part is very important. Whenever you are doing that experiment, while doing that experiment, you already know the collector plate and emitter plate. The emitter plate and collector plate is connected with battery to give the potential. Correct, right? To give the potential to these plates. Whenever you give the positive potential to the emitter plate, positive potential, and negative potential to the collector plate, positive potential to the emitter plate and negative potential to the collector plate, okay, what happens? Slowly the flow of electrons decreases. Correct, right? The movement of electrons reduces slowly, and it will be stopped at one particular negative potential that we know, which is stopping potential. Okay, what we call stopping potential. What is the stopping potential? Which is a negative potential, where we are applying maximum negative potential. This negative potential will repel this electrons flow. Understood? So that is what we call stopping potential. So how much stopping potential we need to apply to stop the flow of electrons? How much negative potential we need to apply to stop the electrons? Electrons will come with some maximum kinetic energy, right? Half mv square. Half mv square is the kinetic energy of the electrons, right? According to this, part of the energy is used to remove the electrons from the metal surface. That is work function. Remaining part of energy electrons will utilize to move with higher speed with some kinetic energy. Correct, right? That kinetic energy is what we call half mv square. Okay, so electrons will come with that much kinetic energy towards the collector plate. This is the collector plate. Okay, while they are coming to the collector plate, if you want to stop that flow of electrons, how much potential you need to give? That we need to find. Okay, so how much potential means that potential energy, okay, it should be equal to half mv square. Correct, right? Because electrons are coming with that energy half mv square. So that energy, how much energetic electrons they are coming towards the collector plate, that much energetic electrons which are coming, the same opposite energy you need to provide. Correct, right? They are moving with the half mv square energy, that is kinetic energy. You should give the opposite same energy, so that both will, the energy which they are coming and the energy we are giving, both will nullify. So that electrons will stop. They will not come. So that is what we call. So I can say that half mv square, it should be equal to, so energy. What is energy in terms of potential? Which is E into V naught. What is E into V naught? Work done is what? What is work done in terms of potential? Work done in terms of potential. What is the relation between work done and potential? Work done is, work done per unit charge is equals to what? Potential. Work done per unit charge is equals to what? Potential. Correct, right? The amount of work done to bring the unit charge is what we call potential. We discussed, right? From infinity to that point. Correct, no? Any point if you want to bring. For example, one point I mentioned. At that point, what is the potential means? How much work you need to do to bring one charge from infinity to that point. That is what we call potential of that point, right? So work done per charge is potential. So work done is what? Energy. Energy is equal to work done. Work energy theorem, you know, right? Change in kinetic energy or potential energy is equal to work done. That's why half mv square is change in kinetic energy, which is equals to work done. So work done will be equal to Q into V. Work done will be equal to Q into V. Now Q is what here? Electrons. That's why charge of an electron. Charge, Q means charge. So electron I am taking and voltage, that is stopping potential V naught. So that's why half mv square is equals to EV naught I take. Understood? Why half mv square is equals to EV naught I taking? Half mv square is nothing but work done. Work done is nothing but change in kinetic energy. Initially, they have maximum kinetic energy. Finally, they will meet at, they will stop, right? They will collect it by the plate. So change in kinetic energy is equals to work done, which is equals to EV naught. Why EV naught we will take? You understood here? Work done per unit charge is potential. So work done is equals to charge into potential. Charge is charge of an electron. Potential is stopping potential. That much potential you need to take to stop the electrons. If you want to stop the electrons to move from emitter plate to, that is cathode plate to anode plate, from emitter plate to collector plate, if you want to stop the electrons, if you want to move the electrons, the movement of electrons can be stopped by giving a potential. Okay, how much potential? That is stopping potential. If you give a negative potential at collector plate, okay, which is V naught, then the electrons will stop. So the photoelectric effect will not happen. Okay? Understood? Okay, so please take this. You understood this concept? Any doubt is there? Please ask. This is easy. Okay. Done now. Once again, I'll explain this. Please listen. Done now? Yeah. So what I was telling is, so since the work done is charge into potential, this much work we need to do to stop the electrons. Okay, that's what. How much it should be? Which is EV naught will be equal to half mv square. half mv square. Correct, right? They will move with very fast, the kinetic energy of the electrons. If you want to stop that fastness, you need to give the work in opposite direction. What we are doing, actually charges can be accelerated by applying a potential difference. Correct, right? If you apply a potential, the charge will flow with maximum fast. If you apply the potential in the opposite direction, the charge will get a repulsive force so that it will stop. That's what we are doing here. Since maximum the charges are coming very fastly due to the incident light energy, we are giving the opposite energy in the form of potential, opposite work. So that because of that repulsive force, the electrons, as they are going very fast, also they are stopping. So photoelectric is stopping. This is what stopping potential is. And you know Einstein's equation, h mu is equals to h mu naught plus half mv square, right? Since half mv square is equals to ev naught, since half mv square is equals to ev naught, what I say is h mu minus h mu naught is equals to half mv square, which is also equal to ev naught. Correct, right? Correct, right? So h mu minus h mu naught means what? Work function W or pi also you can take, which is equal to EV naught. Okay. Now you see here V naught is equals to what? H by E into frequency minus W by E is equals to V naught. Correct? Understood? Okay. So H by E frequency minus W by E into frequency is equals to V naught. Here you can also write V naught is equals to H by E mu minus W by E. So this is something, it is like how this is the equation is look like the equation of a straight line. Y is equals to mx plus mx minus c here. Y is equals to mx minus c. Correct, right? Correct. Now y is equals to mx minus c. So what is the graph you will get? If you take y versus x, x versus y, x is how much? Frequency. Y is stopping potential. How the graph will come? Tell na. What is the graph? How the graph? What is this equation? It's an equation of a straight line. Equation of a straight line. So that the intercept C is negative. Intercept C is negative. So how the graph will be? It is like this. Correct, right? So this is intercept which is touching the negative y-axis, which is minus W by E, minus W by E. And what about this M x? What is x? X-axis which is touching here, H by E. H by E, yeah? Frequency, right? Intercept. So what is the slope of this? What is the slope of this equation? Sorry, straight line. What is the slope of the straight line? See, y is equals to, y is V naught, stopping potential. X is what? Frequency. What is this slope of this equation? M. M is slope now. M is H by E. If you take a slope of an equation, if you take a slope, okay, or tan theta, tangent. Okay, if this is an angle, it is making an angle theta. So tan theta, or you can take a slope. This is A, you take. This is B, you take. This is C. What is slope is? Actually, you can take here A or anything. Slope is equals to what? Slope is opposite divided by adjacent. BC by AB. BC divided by AB, which is always mu naught by mu naught divided by this frequency. So it will be m is h by e. H by e is the slope of this equation. H by e is slope. It is a straight line you will get. Understood? So how stopping potential depends on the frequency, you see. Okay, as the frequency increases, stopping potential also increases. Okay, what is the intercept is W by. Please take. Understood this one? So here what I did is, instead of half mv square, I took EV naught. Okay, EV naught is equals to half mv square. So EV naught is h mu minus W. H by E mu minus W by E is equals to mu V naught, that is stopping potential. So I am using the straight line equation. It is looking like a y is equals to mx minus c. Mx minus c only, no? Yeah. Sorry. Huh? Yes. So this is photoelectric equation, and mu naught is stopping potential, which is along y-axis, and m is x is frequency, so which is along x-axis. So as the frequency increases, as the stopping potential increases, frequency increases, stopping potential increases. Okay, see, at one particular point of see, at zero stopping potential, still frequency is not zero. Correct, right? Stopping potential is zero. Frequency is not zero. Okay, even at, so stopping potential is zero, but frequency is not zero. So frequency will be only negative. It will not be that is negative. Yeah. Why? See, stopping potential is negative potential needed to remove an electron. Even in positive frequency, stopping potential will be negative. H by E, that is not C. Okay, H by E is the slope of that, and W by E, that is work function H, mu naught by E. So work function means what? Negative work function is the minimum energy required to remove the electron, right? Yeah. And what about at that work function, what about the stopping potential, which is negative? Okay, so shall I take the next? Done? Yeah. So now what this is what Einstein's observations, what you understood now. So what are the Einstein's after taking the Einstein's equation, what are the observations you observed? So what Einstein's photoelectric observations. Einstein's photoelectric observations. Photoelectric observations. Photoelectric equation observations. Okay, photoelectric observations. Yes. Can you please tell one? First one is instantaneous. It is. It's a instantaneous. Okay. So photoelectric effect is instantaneous. It is happening very fast. Instantaneous process. Second one, Einstein said, right? So h mu is equals to h mu naught plus half mv square, correct, right? Now mu, h you remove, everywhere h is there, h you take, no problem. Okay, you can take yeah, h mu. So mu is frequency. That incident energy and incident frequency should be, if it is greater than the h mu naught, then only photoelectric effect will takes place, correct, right? You studied this case, right? So frequency, incident frequency should be greater than which frequency? What is this mu naught means? Threshold frequency, correct, right? Okay, the incident frequency should be greater than the threshold frequency to for the photoelectric effect to takes place. If the incident energy is equal to threshold frequency, that time also photoelectric effect will be takes place, because if it is equal to threshold frequency, this half mv square will not be there. If it is greater than threshold frequency, then half mv square will be there, correct, right? If incident energy is greater than this energy, then this will, if this term is equal to this term, then this term will not be there. If this term is less than this term, photoelectric effect will not take place. Okay, understood? Now you write second term. For the photoelectric effect to takes place, for the photoelectric effect, photoelectric effect to takes place, the incident energy should be, the incident energy or incident frequency, please, energy will discuss later, energy also correct, but frequency, the incident frequency should be greater than threshold frequency. What is threshold frequency means? It is a minimum frequency required to remove the electron, correct, right? Threshold frequency for the photoelectric effect to take place, the incident frequency should be greater than or equal to, also you should write greater than or equal to threshold frequency. Okay, threshold frequency, correct, right? Then no, right now. For the photoelectric effect to takes place, the incident frequency should be greater than or equal to threshold frequency. Understood? Next, third one. Can you please tell? Any other points? There are so many points are there. For the photoelectric effect to takes place, what is about wavelength? What is wavelength means? H mu is equals to h mu naught plus half mv square, we know, correct, right? Okay, you write this mu and mu naught in terms of wavelength. C by lambda, frequency means velocity by wavelength. Hc by lambda is equals to hc by lambda naught plus half mv square, correct, right? Okay, now what about the wavelength of light ray? The wavelength of light ray, if wavelength is more, the energy, incident energy will be less, because it is in denominator. If the wavelength is more, energy will be less, correct, right? If the wavelength is less, energy will be more. Understood? Because it is hc by lambda. So hc is Planck's constant into velocity of light. That value will be more divided by lambda. Lambda is wavelength. Now if it is the value of lambda is less, then this will become more because it is in denominator. If it is more, energy will be less. Correct, right? So you can frame the concept. The incident wavelength should be less than or equal to the threshold wavelength. Beyond the threshold wavelength, the photoelectric effect never takes place. Please write. The incident wavelength for the photoelectric effect to takes place, for the photoelectric effect to takes place, the incident wavelength should be less than or equal to threshold wavelength less than equal to threshold wavelength. Done. Above that wavelength, above threshold wavelength, photoelectric effect never takes place, occurs, right? Above that wavelength, threshold wavelength, above that threshold wavelength, if light falls, then photoelectric effect never occurs. Please take. Okay. So these are some points. Now one more point can add about potential. What is the stopping potential, right? If the minimum negative potential, next point, the minimum negative potential, the minimum negative potential needed to stop the photoelectrons. The minimum negative potential needed to stop that potential where we are getting the minimum negative potential to the collector plate. Please remember this, to the collector plate needed to stop the photoelectrons is called stopping potential, correct, right? This is, you understood, right? This is not actually needed, this point is not needed, just writing. Okay, this is already we discussed. Now done. Yes, next one more point. Now fourth point, the photoelectric current is directly proportional to what? Number of electrons increases, Because of frequency or intensity or what? If brightness increases, what happens to the flow of charges? Increases. So photo current is directly proportional to intensity of light. Correct, right? You're right. The photoelectric current, the photoelectric current is directly proportional to is directly proportional to is directly proportional to the photoelectric current is directly proportional to the intensity of incident light, directly proportional, or you can also take the photoelectric current is depends on, also you should write directly proportional, or you can write this, actually the best one is depends on, okay, intensity, depends on the intensity of incident light ray. As the number of light rays increases, the photoelectrons increases. You can see the energy E is equals to NH mu. Correct, right? Okay. So if the energy means if the maximum intensity means, so intensity increases, the number of electrons also increases. Okay. That you observed in the experiment, right? So, and it is depends on the you can hear right here, okay, intensity of incident light and independent of frequency and independent of frequency of light ray, frequency of light ray. It depends on intensity but independent of frequency. See, frequency increases, number of electrons are not increases, only intensity increases, number of electrons increases. Understood? Okay, that's what you understood in that that observation. Next one. The stopping potential is directly proportional to frequency of incident light. Stopping potential is directly proportional to, or depends on, directly proportional to the stopping potential is directly proportional to the frequency of incident light. Frequency of incident light rays. Understood? Frequency of stopping potential increases with increase in frequency. Frequency increases means energy increases, stopping potential increases. I given this, right? Half mv square is equals to EV naught. Okay. Half mv square means h mu. H mu is equals to EV naught. Stopping potential increases since frequencies increases. Okay. Understood? Incident frequency increases, definitely stopping potential increases. Next, one more point. And stopping potential is depends on frequency but independent of intensity. Okay. Any other point? Independent of intensity. Independent of intensity. Okay, one more point you can write. the kinetic energy of the emitted photoelectrons depends on frequency. Okay, right. The kinetic energy of the photoelectrons, the kinetic energy of the emitted photoelectrons, the kinetic energy of the emitted photoelectrons depends on the frequency of the incident light ray, frequency of the incident light ray. Okay, so these are the postulates of Einstein's photoelectric equation. Or okay, you can also write these are the postulates are observations of Einstein's photoelectric equation. Okay, not postulates. Postulates is different. Observations is correct. Okay, but that equation will tell all these things. It is instantaneous process. Intensity doesn't affect the stopping potential. Intensity will increase as the photoelectrons. That means photoelectric current. Stopping potential is independent of intensity, but depends on frequency. Kinetic energy of the photoelectrons depends on frequency. The incident light ray should have the frequency greater than threshold frequency. Then only the photoelectric effect will take place. These are all things. Understood? Understood? Now, can you please tell? Okay, not done. So everyone should tell now that points. Please tell, madam. Yeah. No, by understanding, you tell one point, whatever you understood. Don't see the page. Tell. Okay. What electric current? Uh, 1 minute. Yes. Please take fast. Tell. Okay. Sit down. Now, done now this one. Now I will take the dual nature now. Okay, matter, dual nature of matter. So this is photoelectric effect, what you understood. So basically what is photoelectric effect? Now what you understood I am asking. So what you understood? So light rays are, Einstein's photoelectric equation explains that light particles will come and they will interact with the electrons. Electrons also particles, light particles are also particles. When they collide, they will transfer energy and momentum. Correct, right? Now here they will transfer energy and momentum. So particle nature. So light is a particle. That's why photoelectric effect. Okay, photoelectric effect explains the photoelectric effect explained by particle nature of light. Which nature? Particle nature. Please take it. Okay, we will also call it as quantum theory. This is a quantum theory because light particles are like light quantas. They have energy and momentum. When they will hit, they will transfer the energy to the electrons which are in the metal, and the electrons will come out. Okay. Nature. This is the particle nature. Okay. Now you see here. Yeah. So what you have understood is light is, few people says light is a particle, like Newton. Okay, reflection and refraction. Even Einstein, photoelectric effect. Photoelectric effect basically a particle nature, because as we are discussing, as a light as a particle coming and interacting with electron, it is giving its momentum and energy. Okay, so the electron is coming out. Correct, right? Understood, right? This is a particle nature of light. But you know, Huygens says light is also behaving as a waves, like interference, you have understood, diffraction, and also polarization. Now basically what is the property of the light? Even it's a matter you take. If you take a matter, a material body, will it behave like as a particle or a wave? Means the scientists are telling it's both. It is both. For example, your people are sitting, a body. We are bodies, right? Our body is a huge body. Will we behaving like a particle or a light? Particle. Will we behaving like as a particle or a wave? Particles. So we have mass, we have momentum. Okay, correct, right? Momentum is there. We have mass. That is a particle nature. We will collide. Okay, but will our bodies will have wave nature? Wave nature is also there. That's what the prediction. Even we have wave nature. Okay, if you want to understand it, basically you should go to Heisenberg's uncertainty principle. Okay, so please take the heading uncertainty principle. Uncertainty principle. What is uncertainty principle? What is uncertainty principle? Uncertain. What do you mean by uncertain? Uncertain means you cannot predict properly. Unstable. Not unstable. Uncertain means it is not as accurate. Accurately you can find. It's uncertain. It will change every time. So Heisenberg says the energy and momentum of a particle like electron cannot be found accurately. Correct, right? If you take an electron, the energy and momentum, not energy, the position delta x and delta p cannot be found accurately. That's why it is h cross. That difference is h cross. You cannot find. If you find electron position, then it immediately changes its position. Momentum will be fast different. You cannot find any one quantity. If you find, another quantity will change. One quantity if you find, another quantity will change. For example, electron, for example, it is in a wave form. you can't tell electron is a particle behavior or wave behavior. Okay. So, for example, electron is so fast it is moving. We will call it, the moment of electron as by taking the probability of its position. Okay. So, for example, electron is staying at this position means here the velocity, that means the wave probability will be more. That means the electron probability of position, finding its position will be more. and I will write a maximum probability. So here the electron is there, but immediately electron will jump to the next place. Understood? Electron always move faster, very fastly it will variate. So exactly where the electron it is there, if you want to find, means we are taking in quantum mechanics the probability of finding an electron. Okay, that probability we will take. So exactly where the electron will found in a wave. Okay, that means it will always vary now. So where there is a high peak, where the maximum probability where electron may be present, like that we will assume. If you find the position, immediately the momentum of the electron will be different. So that's why that position and momentum of an electron we cannot accurately find. That is what Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. 1 minute. Okay, it is Heisenberg's uncertainty principle. You cannot find the position and momentum of a particle like electron accurately. You cannot find. If you find the position, momentum will change. Momentum, if you try to find, its position changes. So it's very fast moving. Okay, so that accuracy variation will be there. That is what H cross. H cross means delta x dot delta p is approximately equal to H divided by 2 pi. Okay, this much variation it will be there. What is H value? 6.62 into 10 to the power of minus 34 joules, right? Joule per second. Now, this uncertainty is the reason where you even in the light, okay, and not only electrons, even light, whether it will behave like a particle or light, we cannot explain. That's what dual nature. Light is having two different natures. Why it is still nobody cannot, that much proper understanding is not there. Even if I say, for example, you see electron is coming here. Electron is just falling on the wall. Okay, will the electron maybe see, electron is, for example, one wall is there, electron will come with very fast, electron will come. If it hits the wall, maybe there may be a chance it will penetrate inside the wall. So slowly what happens, its velocity decreases, so it will go like this and it will fall. Understood? Okay, why it is moving inside means it is having a wave nature. Understood? Okay, it is moving, it has a wave nature, and even electron may, why it is going very slow means, so it is sometimes it will act as a particle. When a particle hits the body, a wall, if the particle is so strong, it may be a chance of penetration. It will move inside that wall. Okay. As it moves inside the wall, its velocity goes on decreases. Its velocity goes on decreases. So it is a particle nature, right? And it is also creating waves. Okay. So the duality is there. The duality is there even in the electron, but light, it is much more duality. Sometimes light as a, see, that's what we cannot tell Newton's corpuscular theory is wrong or Huygens wave theory is correct. You cannot tell. Both may be correct. If light is a particle, it will obey reflection and refraction. But it is not obeying polarization. It's not obeying diffraction, interference. Okay, as if you take a light as a particle, it will not obey interference and diffraction. Because if interference should happen, particles will not interfere. Only light as a wave, you will get interference. So that's what dual nature. Okay, and this, even the matter, every matter you see, for example, you take our body only. You are seeing that this body is having material property, like it's as a particle. This is a material body. It is behaving like a particle. Okay, like it is at rest. When it is moved, it will move, like momentum will be there. Where is wave nature? Your wave means you have any like the variation in its cycle? No, right? But we are thinking like that. Our faculties, our eyes, we cannot observe the wave nature of even the material bodies. Okay, every body in the nature is having dual wave nature also will be there, not only electron, but maybe because of the maximum size and mass they have only particle nature we are seeing, but every body is having even both particle nature and wave nature. That's was the conclusion. Maybe our eyes we cannot see properly. Electron is having both particle nature and wave nature. Understood? So what is particle nature means? For example, a particle you take, one body you take, it will go and hit the wall. As a particle, what is the conclusion you should give? It will bounce back. Correct, right? If the particle goes and hit the wall, what will happen? It will bounce back. So what will be there? It is momentum. Mass will be there and velocity. Correct, right? Momentum will be conserved, right? Initially it will go, again it will come back to the same place, is if it is a particle. Okay, but if it's a wave, if it's a wave, it will go and it will penetrate. Am I right? Okay, so wave means it's a transfer of energy. Now, particle wave we can write, see for example, a wave is going like this. 1 minute. Yes, now you see, you know, right, waves starting like this, it will go, it is a sine wave I am taking. You see here, as the it is showing a wave nature means, okay, so you know from one crust to alternative crust or trough is having lambda wavelength. Wavelength is the length of the wave and momentum is the particle. Particle nature is momentum. The momentum will show only for the particles. The wavelength will show only for the waves. Correct, right? A momentum will be there only for the particles, because a particle, if it is fall on any on surface, it will have conservation of momentum. It will show the momentum character. But when a wave is created, it will have some lambda and its frequency. Okay, lambda means wavelength and its frequency, it will move with some velocity. Now, if the material bodies, objects, if we have both dual nature, then how we can give conclusion? That's what the same Heisenberg uncertainty principle is used by the another person by name de Broglie. De Broglie. You heard about him? De Broglie is the first person who is the first scientist who given the relationship between particle nature and wave nature. They are related. Why light sometimes behaves as a particle? Why sometimes light behaves as a wave? Why electron sometimes behaves as a particle? Why electron behaves as a wave sometimes? He given the connection. He mixed both. That is what de Broglie's uncertainty principle. It is a hypothesis. It is a hypothesis. Hypothesis means what? There is no exact proof. It's a imagine a thought. He given that equation by something, but we didn't prove it. We cannot prove it. It's a hypothesis. He made a hypothesis, not experimentally verified. Understood? So that is what the next thing. Here we taken for electron delta x and delta p is h by 2 pi. What de Broglie says, okay, the position and momentum here is given now. Okay, that means particle nature is what? Momentum. Particle nature is what? Momentum. And wave nature is what? Lambda, wavelength, is again related with h. This is what de Broglie. See, position, particle and wave nature you cannot predict. It is uncertain, like Heisenberg's uncertainty principle. Okay, he said for electron, position, momentum. And even also he said there is variation in time and energy for an electron, h cross. Here also you can write h cross. Okay, so he says lambda is equals to h divided by p. This is what Heisenberg's uncertainty, sorry, Heisenberg's alla, de Broglie's wavelength. De Broglie wavelength. Okay, please take this. I will discuss this more, that de Broglie concept. Please take. What is de Broglie hypothesis means? He given an hypothesis which is connecting the wave and particle nature of the light. Okay, you cannot exactly predict the particle and wave nature when it will change. Okay, so it is del lambda is equals to h by p. De Broglie wavelength is equals to h by momentum of the particle. So every particle is giving a wavelength, you see, lambda. That means a particle is also behaving like a wave. That's what he is telling. Understood? A particle is also behaving like a wave, and a wave is also behaving like a particle with a value which is h or h cross, which is 6.625. This is Planck's constant. Understood? It's a Planck's constant. Please, shall I take next page? Yes, please see your slide. Right. Yeah. Now he says, so de Broglie hypothesis. What is de Broglie hypothesis says? According to de Broglie, every material particle will behave as a wave, okay, and with the de Broglie wavelength. Every material particle or every particle also, every particle at one point behaves as a wave, particle nature will become a wave nature, behaves as a wave, yeah, behaves as a wave. Alright, what happened? Yeah, it's not coming. Every particle is behaving as a wave, and the wavelength of the wavelength of a particle okay, or a matter, the wavelength of that particle which is a material, correct? No, that's why dual nature of matter and waves. Okay, that, what is the chapter name? Matter and radiation. So this matter, a material particle, the wavelength of that particle which is showing dual nature is given by, dual nature is lambda, which is equals to h by p, where lambda is called de Broglie wavelength. De Broglie wavelength. and what is P? Momentum of a material particle. Momentum of a particle, material particle. And what is H? Which is Planck's constant, which is approximately H is equals to 6.625 into 10 to the power of minus 34 joule second. Because of this small energy per second, okay, the particle will try to, it is looking like a wave. The particle nature is like a wave nature, and wave nature is like a particle nature. It's the variation. So body, a particle, material body, a material particle will behave as a particle as well as a wave. The dual nature is there. Even light is there. Sometimes light acts as a particle, and sometimes light acts as a wave. Okay. That's what de Broglie, it is a hypothesis, and he got a Nobel Prize for this. Okay. De Broglie got a Nobel Prize for giving this equation, which is connecting the particle and wave nature of light or a matter. For matter and light also. Matter means you take electron, for example. Electron is a matter. It will behave as a particle as well as light. That duality is there. Understood? That's why the name dual nature of matter and radiation. Radiation means light. Light is a one form of radiation, right? Yeah. Joule per second it is. Joule per second. So, understood this one? Yes. So, please take one question. Find the there are so many, still more things are there to discuss. We'll discuss. Find the, I will take question now. Then find the wavelength, or de Broglie wavelength. You know what is de Broglie wavelength, right? What is de Broglie wavelength means? It's a wave nature of that particle. De Broglie wavelength of okay, light particle, a light particle of mass 9.1 into 10 to the power of minus 27 kg, and velocity 2 into 10 to the power of 8 meter per second. Please find. Given H is equals to 6.625 into 10 to the power of minus 34 joule per second. Do it. Do this. Easy question. Hmm? Hmm. Velocity is, find it, easy it is. Do it first. So here what is the given? Just see, solution will do. So the thing is what they given, velocity, okay, v is equals to how much? 2 into 10 to the power of 8 meter per second. Now mass is 9.1 into 10 to the power of minus 27. This is a what? Mass of 9.1 into 10 to the power of minus 31 you take. It's mass of electron. I am not 27, it is 31. 31 kg. Okay. Minus 31. Now, what is the de Broglie wavelength? Lambda is equals to what? H by P. P is what? Momentum. H is Planck's constant. So H divided by momentum is mass into velocity. Okay, easy it is. Now 6.625 into 10 to the power of minus 34 divided by mass is how much? 9.1 into 10 to the power of minus 31 into velocity is 2 into 10 to the power of 8. Do it and tell the answer. Whatever the answer you will get, that is in meter. Lambda wavelength is in meters. Okay, how much you got? Plus 31 go 2.8 will go up minus 3 means 10 to the power 5. So 10 to the power 5 will come and this you do 9.8, 6.65. So tell the answer, how much will get? What? 36.4. What is 9.1 into 2? 2. 6.625 divided by 18.2. Do it. 0.364 into 10 to the power of minus 5. Because 8 is there, this 31 is there, this is minus 3 plus plus 3 minus 8 is minus 5. Okay. So it will be, I can also write 3.6 into 10 to the power of minus 6, okay, meter, very less, micrometer. This is the lambda de Broglie wavelength of an electron. So electron velocity is not 2 into 10 power, but I am taking just. Okay. Now take a similar type of problem. I will just give a data. Here light of the particles this one, mass I will give 0.12 kg, 0.12 kg and velocity is 20 meter per second. 20 meter per second. Now what is the de Broglie length? Find it fast. Meter per second. So you can write here. Shall I write? You do it. So So H is 6.625 into 10 to the power of minus 34. Next. Next, this one mass is 1 2 into velocity is 20. How much will you get this? Into 10 to the power of minus 34 meter. Very less, no? That means as the mass increases, what will happen? The wavelength is very less. As the mass increases, what will happen? The wavelength is very less. This shows that even a material body like a ball of 0.12 kg, okay, this is a ball trick, it will have a wave nature, but very less. It is also having wave nature. Every particle, even your bodies also show wave nature, but very less. Every particle, if the mass is more, wave length is less. That means wave nature is less. If the mass is very minute, it will have more wave nature. Understanding? Understanding or not? Wave nature is there when the mass will be more. The mass is less, wavelength is less. This is the Einstein's, de Broglie's, okay. And one more thing is there, we need to do the problem based on Einstein's photoelectric equation. We will do it in the next class. And we also want to do problems on Einstein's photoelectric equation and also stopping potential. So then you will get a better clarity, okay. So yeah, we'll meet in the next class, okay. Thank you. Thank you.